I'm standing here today in Alberta's industrial heartland. This is just one of the many places across North America and globally where members of the Canadian Crude Quality Technical Association operate. I'm Dave Murray, Secretary of the CCQTA and Principal Consultant at Omnicon Consultants. Today we're going to take a brief look at the evolution of the CCQTA from its inception into what it is today. Before I get too much further, I should briefly talk about what I mean by crude oil quality. The term crude oil quality likely has many definitions depending on where you are in the crude oil production, transportation, refining, and/or purchasing chain. 3 crude oil quality parameters are generally used to determine the value of a crude oil. These are density, sulfur, and TAN, or total acid number. Historically, it has been generally accepted that low sulfur density and TAN crudes are easier to handle and/or refine, which implies good quality and good value. Let's look at this from another direction. Broadly stated, quality is the degree to which a product or service meets the expectation of the end user. Processability is loosely defined as any aspect of the production, blending, storage, and/or transportation of crude oil which impacts product handling. In a more practical sense, it is associated with minor changes in crude oil composition, which could be insignificant to one sector, but potentially detrimental to another. Processability issues are often the result of trace-level contaminants of the crude composition. These tend to be relatively low concentration, but they build over time, often resulting in expensive remediation efforts. These contaminants are becoming more and more important in the crude selection process, and they're a key area of focus for the CCQTA. What factors can impact crude oil processability? Each sector of the industry has their own goals and guidelines when it comes to crude oil handling. A producer will want to ensure that the product meets pipeline specifications. Next, the pipeline must be able to move the product without impacting pipeline integrity or infrastructure such as pumps, meters, and tanks. Unfortunately, some of the practices employed in one sector can have an unwanted effect on the downstream sectors. For example, while the injection of additives can enhance production, it may also have a negative impact on the refinery receiving the product. Similarly, crude blending into pools can maximize tankage and pipeline utilization. However, some crudes are not compatible with one another, creating blend instability, which can upset or foul downstream units. Let's have a look at the various activities that can impact crude oil received at the refinery. The first link in the chain is production. Changes in production methods, such as changing from primary to secondary recovery using enhanced oil recovery techniques like CO2 injection, or introduction of new production techniques such as SAGD and/or solvent enhancement. Also, the use of new additives or changes in chemistries and/or the concentration of existing chemistries in use. Also, slop management methods, like is slop being injected back into the sales quality product? Then we move on to blending. Blending is often done to meet or target established specs. This can include the injection of products like butane, condensate, crude oil, etc., depending on if the desire is to blend up or down in density, sulfur, or TAN. Next in the chain is transportation. Batch interfaces, interim storage, tank cleaning can also add to existing solids in the crude oil. Changes in pipeline operating conditions, such as stop or intermittent flow conditions, can result in batch interfaces mixing, water and solid settling, etc. Also, injection of truck material can also have an impact because they're small batches of different production that may cause spikes of one or more parameter that are unanticipated by the refiner. Next is waste oil handling. Waste oil is typically treated to remove identified contaminants to meet pipeline specifications, but is not likely to remove all contaminants, especially if they're not known or expected. And lastly, even refining can contribute to contamination through activities such as on-site blending and storage and slop handling and reprocessing. Ultimately, the refiner needs to know what the molecules will be that are delivered to the refinery, and if those molecules can be turned into finished products such as gasoline, diesel, jet fuel, etc. Any additives or contaminants that are not deemed acceptable in the final finished product may have deleterious effects on either finished product quality or production. All these factors led to the formation of the CCQTA to provide a technical forum for members of all sectors of the industry. The goal is to have all sectors represented and to work cooperatively together with a common goal of identifying and resolving potential issues related to crude quality. Within the CCQTA, cross-sector education is a very important aspect of the association's work. It is valuable to get input from someone within the production community when trying to identify a source of contamination in a refinery. Conversely, it is beneficial for production personnel to learn more about refinery sensitivities. At the same time, it's important for additive suppliers to see both sides and try to balance upstream benefits with downstream impacts. Pipeline involvement is also critical, as they are often the gatekeepers of product specifications as a transportation link between production and refining. Next, the laboratories, research organizations, and consultants are encouraged to participate to provide the analytical and testing support for characterization and identification. The association was founded on the following educational and scientific objectives. An association focused on identifying and addressing existing and potential crude quality-related processability issues, comprised of members from all sectors of the oil industry in order to facilitate the association's work and ensure that all sectors' interests are represented, and finally to improve industry knowledge and awareness of crude quality issues. In 1996, an industry-based crude quality technical committee was established to discuss common crude quality issues. At that time, 3 key projects were in progress, including a refinery issue with phosphorus fouling, which had surfaced in 1995. Next, the development of an additive screening methodology. And lastly, an organic chloride investigation carried out by 2 industry members. In 1997, the Ad Hoc Industry Committee was formalized as an association under the Societies Act of Alberta, and the CCQTA was born. These are the guidelines that the CCQTA operates under. Operations are governed by our bylaws under the Societies Act of Alberta. The membership is represented by 7 sectors of the oil and gas industry, including producers, refiners, midstream, transmission pipelines, additive suppliers, government agencies, industry services, and international members. As a strictly technical association, we do not permit discussion related to trade, pricing, or financial transactions, etc., based on our antitrust guidelines. The association was originally structured to facilitate participant-funded projects. However, now the majority of our projects are CCQTA sponsored. All the activities of the association are funded via annual membership fees. What kind of people make up the CCQTA membership? The CCQTA is comprised of members from diverse technical backgrounds. This includes engineers, chemists, technologists, researchers, operations and logistics personnel, government and regulatory staff, technical sales, and that's just to name a few. Between 1997 and 2015, the association simply functioned as a vehicle for members to propose group-funded GIPs. Some projects had only 2 or 3 participants, while others involved over 20 member companies. All of the data and results initially belonged to the participants, with the understanding that reports would eventually be made available to all CCQTA's members 5 years after the projects were closed. Some of the work resulted in publication of documents on very industry-sensitive subjects, such as naphthenic acids, olefins, organic chlorides, H2S, and light ends and vapor pressure measurement. During this period, membership reached as high as 74 members. Over 20 individual projects completed, of which the majority include final reports which are now available to all CCQTA members. 5 test methods were developed and or revised, and 2 white papers were published. Once it became apparent that much of the CCQTA's work was of interest to the industry, the association restructured to a membership-based funding model, which then provided input and data access to all members. By virtue of the association's increased profile outside of the CCQTA, we've been more involved with industry groups such as ASTM, API, NACE, ISO, the National Academy of Science, Sandia National Labs, and many, many more. Under this new operating model, the CCQTA has managed 26 projects, published 12 white papers, developed 6 ASTM procedures, 2 reports, 1 best practice, and 1 guideline. Proper sampling and testing for H2S and vapor pressure has been the focus of many of these documents, and many of those are posted publicly on the CCQTA's website for the benefit of the industry as a whole. Communication and education has always been a key component of the CCQTA's mission statement. We regularly hold project meetings, including a quarterly open forum meeting to discuss current issues and review new project ideas. We do capture minutes and distribute the minutes of all our meetings. However, in recent years, we've also increased our efforts at communication by publishing a quarterly newsletter. Through the newsletter, members get regular updates on all our project work. The newsletter also contains links to the individual project milestones and recent updates publicly posted on the CCQTA website. More recently, in 2020, we have begun publishing a series of Lunch and Learn videos as an educational endeavor to provide information to members and to the industry in general on topics that the CCQTA has been involved with. Some of the Lunch and Learns are publicly available and are focused on topics the association feels the whole industry can benefit from, while others are only available to CCQTA members. These videos are intended to act as an internal training session for members on key subjects of general interest. They usually include a summary of the association's work and help keep members and their peers informed on the latest developments in key areas. Members can bring any project idea to the association. For example, a refiner may have an issue with fouling and deposition that they suspect might be related to their feed. They present their concerns to the group during an open forum meeting, looking for interest in launching a project. Members from the various sectors express their interest. If there is sufficient interest in the topic, then a project is initiated, project manager is selected, work is planned, and budgets are developed. The funding structure for a project is dependent on the level of interest amongst the various sectors. If there is widespread interest across the various sectors, the project will be sponsored by the association. If the project is very narrowly focused between only a few sectors, then the project may be initiated as a participant only and operated independently.
Having spent 33 years of my career, all of my career working in the downstream in the refineries, providing support for desalting and corrosion control, like Andre, the one challenge that we had is we're very myopic. We live inside the gates of the refinery and don't have a good sense of what the quality of the feedstock is coming down the pipe. We just receive it and it's problematic and we don't know why, we don't know how. CCQTA to me gave me that link or provides me with that link of how I can try to better understand what's coming down from production, from pipeline and transportation, and how that impacts the refinery, which allows us to better implement our solutions to help the refiner have smoother operations. And that's what it is to me. The first thing it is to me. The second thing to me is the atmosphere of CCQTA. I've gone to a lot of conferences and you get a lot of advertising, you get a lot of marketing, you get a lot of show and tell, you get a lot of people promoting themselves in the business. When we have these get-togethers, it's a lot of really smart people that just want to talk about the technical issues, communicate back and forth, help each other understand, and build our knowledge and collective knowledge so that we can improve the quality of the feedstock that comes down the pipe out of the ground into the refineries. So for me, that's a huge benefit. It's a technical conversation. There's a lot of freedom of exchange of information, a lot of openness. We're not worried about proprietary as much, and not as stressed about that. And we share more openly. So there's great communication. I think that's an extremely powerful tool that CCQTA uniquely provides that you can't find in other associations.
As I've mentioned, the CCQTA has worked on many projects over the years. I'm going to highlight a few of our projects that have had a significant impact on the industry. Let's start with the phosphorus and crude project that launched the CCQTA. Phosphorus fouling began to surface in Canadian refineries in the mid-1990s due to the use of dialkyl phosphate ester gellants in hydraulic fracturing operations. When DAP enters the atmospheric crude tower of a refinery, they result in fouling within a narrow temperature range. These 1995 and 2002 videos taken inside primary and secondary crude distillation towers highlight the level of fouling caused by phosphorus. The holes shown have a normal diameter of 1/2 inch, which in many cases are reduced to 1/4 inch or less, which severely limited the throughput, resulting in unplanned shutdowns. From 1995 to 2005, the CCQTA conducted extensive root cause analysis, method development, sampling and testing work, and determined that DAPE was the cause of fouling and identified several sources where they were entering the crude network. Based on this work, in 2005, the Canadian Association of Petroleum Producers, or CAP, implemented a specification to limit the amount of volatile phosphorus permitted in sales quality crudes to 0.5 ppm by mass. Combined with new product development work by additive suppliers, phosphorus-linked fouling issues began to subside during the mid-2010s, both in Canadian and U.S. refineries. However, in recent years, phosphorus fouling issues have resurfaced in a different temperature range, and the CCQTA is now actively working on identifying the source. Now let's look at the oil sands bitumen processability project. In 2006, the CCQTA launched this project to assess potential refinery processability issues with the newly developed Alberta dill bits and syn bits. U.S. refiners, based on historical challenges running conventional Canadian heavies, were concerned about processing these newer, heavier products. Detailed project work involving refiners, producers, and chemical suppliers ultimately determined that the processing issues would be minor, which facilitated the acceptance of dill bit products into the U.S. market. In 2012, some of the project data was provided to the National Academy of Sciences in their investigation into the impact of diluted bitumen on pipelines.
Hello, I'm Keith Lawson. I'm the Director of International Members, and I'd just like to talk about the Oil Sands Bitumen Processability Project, and that was managed by the CCQTA, and we found it really valuable because we were battling with the acceptance of these newly arrived synbit and dilbit crudes. And we managed to do that, and some very specific concerns about how they caused fouling and how they corroded in crude towels were put to rest.
Next, we'll take a look at vapor pressure and light ends. This project was initiated in 2013, primarily due to conflicts between measured vapor pressure data and the API nomograph conversions from RVP that were used for EPA tank emission calculations. A significant volume of data was presented comparing the prominent ASTM D323 RVP method versus the newer ASTM D6377 method. In the end, the project work extended out well beyond test method comparison into the impact of sampling methods, as well as the methods used for compositional analysis. Overall, between 2014 and 2018, this project spawned 2 ASTM test methods plus 2 ASTM standard practices. In 2017, the CCQTA also published a vapor pressure best practice summarizing the project findings. And in 2021, released 2 educational videos. Based on the findings of this project, the industry has also moved away from the legacy ASTM D323 method and adopted the more accurate ASTM D6377 method. And lastly, we come to pipeline sour service. This project was initiated in response to regulatory changes in how pipelines were designated for sour or non-sour service, meaning H2S or non-H2S, and specifically related to sulfide stress cracking. Prior to 2007, CSA Z662 included a sour service exclusion for transmission pipelines based on a pre-2003 version of NACE MR0175. In 2003, MR0175 was harmonized with ISO 15156, and the exclusion clause was removed. Subsequently, when CSA published an update to Z662 in 2007, it also harmonized with MR0175 and removed the exclusion clause for transmission pipelines. This left the transmission pipeline community in a very difficult position with hundreds of thousands of kilometers of pipelines that were not built for sour service. In 2015, the CCQTA undertook to assist the industry, which had been struggling to find a solution to this regulatory problem. A significant amount of monitoring and physical test work was performed to show that SCC is not possible under the conditions that a transmission pipeline operates, as well as to provide a scientific basis for that argument. In the end, a large amount of operational data was provided by the major pipelines, showing that in 70 years of operating history, no transmission pipeline has ever experienced sulfide stress cracking. This data was presented to the MR0175 maintenance panel with recommendations to revise the standard with an exclusion for transmission pipelines. In 2021, ISO 15156 and NACE MR0175 was revised with the requested exclusion in place. Currently, the requested revision to CSA Z662 is in progress.
I'm Ashutosh Garga, and I'm the CCQTA Director for Alberta Energy. Over the years, the department's continued participation in the association has provided three main benefits. Number one, it has enhanced our understanding of crude quality issues for the transportation of Alberta's crude oils. Number two, it has enhanced our knowledge of the technical merits of the oil sands industry's ability to undertake value-added investments. And three, it has provided valuable input to help support one of the department's key priorities, to pursue and advocate for increased market access for Alberta's energy products. We have also received tremendous benefit from specific CCQTA projects. For example, both the bitumen dewatering and total acid number projects helped us identify key considerations for assessing Alberta Energy's oil sands policies and regulations governing oil sands royalty collection. Membership in the CCQTA has been an asset to our department's work. Thank you.
I hope this has given you a good taste of what the CCQTA is all about and what it has accomplished over the last 25 years. If you'd like further information about any of the other topics the CCQTA is working on, please visit our website at www.ccqta.com. If you have any feedback or questions, please send them to secretary@ccqta.com.